Podcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Welcome on the behalf of American Membrane Technology Association and Toray Membrane USA. I would like to welcome all of you to today's webinar, PFAS Separation, Concentration, and Destruction, the Entire Cycle Explained. My name is Kendra Spires. I will be moderating the webinar today, and I am the Marketing Manager for Toray Membrane USA. Our webinar today is hosted by AMTA and Toray Membrane USA, and we are excited to be joined by today's panel of experts. We got two of them, and in today's webinar, there will be one presentation presented by Sean Carter and then Zia Cloakey. Following the presentation, there will be a 15-minute Q&A session, and if there's more questions, we will go past that, but be ready with some questions. I'd like to go over a few housekeeping items before our first presentation. First, all participants are muted for the webinar. If you would like to switch your audio from your computer to your phone, use the control panel located in the upper right corner of your screen. Select the telephone in the audio panel, and the dial-in information will be displayed. You will have the opportunity to submit text questions at any time during the presentation. Select the questions from the drop-down menu towards the bottom of the control panel. Questions will be collected and addressed during the Q&A session at the end of the webinar. You can download today's presentation by clicking Handouts in your control panel and saving the PDF files to your computer. At the conclusion of today's event, please take our survey. We encourage your engagement and feedback. So let's get started. I'm going to introduce Sean and Zia. Sean Carter is the Sales Director of North and South America for Toray Membrane USA. He is a BS in Mechanical Engineering from California Polytechnic State University. He is a licensed professional engineer in the state of California in mechanical engineering, fluid and thermal systems. His experience includes design and construction of a large and small scale reverse osmosis, ultrafiltration, and MBR water. Zia Cloakey is a PE and is a product manager for Ovivo's PFAS Solutions product group with a focus on absorption, IX-GAC for PFAS treatment. Ms. Cloakey holds a bachelor's degree in chemical engineering from 2018 from the Oregon State University. She joined Ovivo in 2023 as a research engineer, initially focused on identifying and developing and optimizing new and emerging PFAS concentration technologies, foam fractionation, regenerable ion exchange, etc. She has now transitioned to a product management role with a focus on absorption technologies and how they can be leveraged and integrated into a complete water treatment solution with on-site PFAS destruction at its core. We're going to begin the presentation here, and we'll pass it on over to Sean.
All right. Thank you, Kendra. I'll just take a moment here to share my presentation, so just bear with us one moment. There we go. All right. So thanks everyone for joining us today. We're going to be talking about PFAS here, and we originally worked on this with both Zia and Katie from Ovivo, and unfortunately Katie's quite sick today, so Zia is going to be giving that portion of the presentation. But we're going to be talking about the separation, concentration, and destruction cycle, right? You know, it's obviously a big topic in our industry, so we wanted to give some background from our perspective, what we're seeing as, you know, solutions providers and where we see this market going. Let's see here. Okay, so let's talk a little bit about what are PFAS, right? So PFAS are these manufactured chemicals that have been used in industry since the 1940s. So very, very common. We've all been exposed to them. There's widespread exposure amongst our population and amongst our waters. And you can find PFAS in the blood of people and animals all over the world at this point. So there's essentially full spread of these compounds amongst our society. And when we first started talking about these 5 years ago, we wanted to understand what is it that we're talking about. So what we're talking about is per and polyfluoroalkyl substances, right? So this is a family of chemicals, and it's a fairly broad family of chemicals. And they're all synthetic organofluorine chemicals. So if we're going to try and define that here, if we're talking about organofluorine, what are we talking about? That means it must have multiple fluorine atoms and that they are attached to an alkyl chain, right? So that means you've got a carbon chain, and you've got fluorines directly bonded to the carbons on that chain. And the alkyl chain refers to the carbon chains that forms the backbone of the molecule. And there's a couple of examples there of different variations. Any of those intersections of the lines there, that just signifies where the carbon is in that bond for any of you with organic chemistry backgrounds. So, you put these two things together, and we have all sorts of examples of carbon fluorine chains that can take all sorts of forms. So this particular example here is a PFAS, which is a fluorosurfactant. I remember as a kid, growing up and going skiing and spraying my clothes with Scotchgard to make them waterproof. And that seemed great at the time, and knowing what I know now, maybe not so awesome that we were spraying our clothes with a carcinogen, right? And Scotchgard itself, that this particular chemical is currently illegal in California and Maine, and obviously we're seeing more and more legislation that will limit and or prohibit the use of this type of chemical going forward. Another example, which there are documentaries out there on, is PFOA, which is also known as C8, known for its 8 carbon chain structure. So it's a carboxylic acid, and is used as an industrial surfactant, primarily used to make Teflon, which is, as we know, very, very widely used. And if we're talking about how is Teflon made now, the manufacturing method has changed. They have changed it from C8 to Gen X was the next generation used after C8. However, Gen X is also in the PFAS family and has, as far as we are learning, some similar negative effects. So, why were these chemicals used in the first place, right? The carbon fluorine bonds are one of the strongest single bond in organic chemistry, right? And so what that means is these chemicals are very, very stable, which if you're making chemicals is usually useful in industry. It means they're less susceptible to breaking under exposure to other chemicals, right? So, if any of you have ever worked with some of these in the past, that's why they work, is that they do not break down under the presence of other chemicals or oxidants, that sort of thing. And they typically do not break down under heat exposure. And I'm talking about moderate heat exposure. Under extreme heat exposure, incineration type temperatures, you can break these carbon fluorine chains, but heat is not an especially effective way of breaking these chemicals down. as surfactants, they could resist water quite well, right? Thus the Scotchgard use, and they could prevent bonding of food with pans. They could also prevent bonding of food with wrappers. So we've seen a lot of PFAS be used in food containers over the years as well. So I bring all this up because all of these things are quite useful if you're a chemical supplier. But there's some downsides here that we've learned over the years, and because of this, the main reason why Teflon was used in non-stick pans. They use this example, happy pan. I mean, I guess not so happy if you have cancer later from it, but as fun as that sounds, this is why things are moving away from this direction. But what are some of the negative effects that are documented? Pulled this off of the EPA site. How dangerous are PFAS chemicals? Well, it turns out they're quite dangerous, and they're quite dangerous in very, very, very low concentrations. So cancer effects, reproductive effects, among other issues from these chemicals. And so that brings us to, okay, so we've identified these chemicals. We understand they're prolific in our environment, in our bodies even. And what is the North American situation? And in the U.S., it is quite widespread, partially because DuPont and 3M were companies manufacturing this on large scale in the U.S. And so if we look at the map, anything that is a light blue is a drinking water that we already know is above the EPA limits that are coming out for PFAS. So, but because of this manufacturing, especially on the East Coast, that's why you see so much on the East Coast, right? The East Coast also has larger rivers than we have on the West Coast. This manufacturing of specifically these PFAS chemicals on the East Coast led to widespread pollution of the ground and surface waters, especially in eastern states, but in western states, we also see quite a lot from firefighting efforts. The original foams that were used to be dropped from planes for fire suppression were made from PFAS. So there's many communities on the West Coast where the groundwater and the streams were directly polluted by firefighting efforts, unbeknownst to us at the time. So if we're talking about these chemicals, they're also called forever chemicals. And that's because they persist entirely through the cycle, right? So if you have it in a reservoir, that would go to your water treatment plant. Standard water treatment plant, unless it has RO already, is going to pass that PFAS, RO or carbon. Then that PFAS is going to pass right through. That means it ends up in the drinking water, it ends up in the landfills, also leaches out of the landfills, and even that landfill leachate that's treated and ready for discharge, up until very recently, until now, there hasn't been a focus on the removal of PFAS from these waters. So we have to actually use the technologies to remove this. Standard water and wastewater treatment technologies do not typically remove these constituents. So we have to make this effort. And here are those EPA drinking water guidelines that are coming. So we've got PFOA and PFAS. Those are the two most common, the two longest chains. Those are the easiest to remove. They have their 4 ppt limits, and that's 4 parts per trillion. So these are incredibly low concentrations, right? And then other PFASs, I mentioned there's a wide range of PFASs. I think over 6,000 have been identified. And for any of the other remaining ones, a lot of these fall under hazard indexes. And so the EPA is still figuring out how we're going to regulate this, but this is the guideline that's been sent out. And public water systems have until 2027 to complete their initial monitoring. So we're still even learning about all of the places where this pollution exists. And even then, they have only until 2029 to implement solutions that reduce these PFAS if drinking water limits exceed these MCLs. So the requirement to address this problem is very close to us already. And when we're talking about these, PFAS removal technologies, there's multiple different ways of performing this. But when we're talking about reverse osmosis or nanofiltration, we're talking about liquid to liquid separation, right? And compare that, and I'm trying to make that distinction between that and a solid to liquid separation, which would be the case in terms of carbon or resin style of separation. So if we're going to talk about carbon just real briefly, right? Carbon is an absorption technology. It is the cheapest initial cost. That's nice. But what are the downsides? There are enormous disposal concerns, right? And the historical problem with carbon is, yes, it captures some of these PFASs, but it doesn't catch all of them. And then even in the ones that it does, now you have a disposal problem with carbon. You've got a contaminated media that you have to get rid of. They do have quicker breakthrough with carbon compared to the other technologies. And it's effectively not very good at small chain removal, right? The longer the chain, the more clumsy that molecule, and the easier it is for it to get caught in essentially the holes of the carbon. So small chain removal is quite ineffective, and huge volumes required, right? Huge volumes of carbon, and that can mean real estate on the water treatment plant site, which maybe they don't have. But again, that huge volume also goes back into the disposal issue. And we've seen resin come into this space as well, and resin's made quite some good progress. It does have higher removal capacity than carbon. It's sometimes absorption only. So a lot of the original resins for PFAS were absorption only, but that means replacement is still required. It is higher cost than carbon, but typically lasts longer. Some are regenerable, but the regeneration can be quite expensive. And there's varying contact times, et cetera. So, we see resin playing a piece of the role in this PFAS separation scheme. But from what we're seeing, I think RO is going to play a very big role as well. And what about RO, right? So, in terms of separation, it has the best separation for all chain lengths. And this is a big area of R&D for Toray. Compact footprint, that's nice, right? We all know how big an RO system is and what how much water you can get out of a given space, and it is quite efficient in that regard. I'll comment, we're getting better at it, right? If you had asked us 3 years ago what our rejection rates were of different PFAS molecules, we kind of look at you and say, I don't know, give it a try. We can make a guess based on its molecular weight or its whether they don't have much surface charge, which is the primary method of rejection for RO. But we could make some educated guesses, but we didn't have a lot of data. But we have been gathering data in recent years. And keeping it in the aqueous form, liquid to liquid concentration, does manage your liability, right? You don't have this disposal issue that you have potentially with some of the other products that are out there designed to help with this issue. Now that doesn't mean you're done with RO, but that means this might be one of the key steps in getting us where we want to be in our treatment scheme. And since I am from Toray and we focus on membranes, I would like to talk about membrane separation, specifically with PFAS and other low molecular weight, low surface charge constituents, and talk about what are we doing to figure out how to better reject PFAS with our membranes. You know, with any membrane, you're trying to get to this optimum goal where you're trying to pass as much water as possible and prohibit as much dissolved constituents as possible. And the best way to do that is to make your polymer chains as consistent as possible, right? You know, we call it polymer chain cross-linking. So this is the when you make an RO membrane, you're effectively making a polyamide. A polyamide is a cross-linked polymer chain. And what you're trying to accomplish there is you're trying to make this these chains very consistent, and you want them to you know, the more uniform that you make it, the better that you will ultimately get with your combined water quality and energy savings simultaneously. And if we look a little bit closer at these membranes with some of our equipment here, our scanning electron microscopes, you know, you can see what that membrane surface actually looks like. Now the membrane thickness is super thin, right? I want to say it's around the 20 angstrom thick range for the actual thickness of the polyamide. So super thin. And you can see that cast on top of the polysulfone layer below that, it actually isn't as smooth as you might imagine, right? It has what we call these protuberances and interstices, which are these peaks and valleys that we see in that polyamide. And breaking that down further, right? It is very important to have a more consistent distribution of thickness, right? Because if you have thin areas, that is where most of your salt passage will occur. And if you have areas that are too thick, then you will not get sufficient water flow through those regions. So the goal is to make a very consistent but also very thin polyamide layer, and that's going to give you the best performing membrane that you can make. So Toray spent a lot of time and effort in understanding these protuberances, how they form, how to control them, how to make them as consistent as possible. And this is really neat. These are some images that we've only made public in the last couple of years, but they're quite extraordinary. And I've actually been to the R&D plant in Shiga, Japan, where we have the microscope that took these pictures. But this is the cross section of the protuberance. As you can see, we're already 20 nanometer scale, which is extremely high resolution. But this microscope can go all the way down to 2 nanometer scale, which is nuts. Because what you're looking at in the image in the right is those are the actual polymer chains of the membrane. So you're seeing atoms there, right? Which is really extraordinary that we can see this. And there'd been some debate in the past about whether or not a membrane is a solution diffusion model, or if it should be a pore model. And we're quite confident it should be a pore model because, we can see the pores. What does this lead us to, right? Why are we taking these pictures? Why are we spending this money to do this? Well, it's important for us to understand that cross-linking on a very intimate level and understand what changes that we can make increase the cross-linking and make that better. So you can see conventional RO on the left and our newest generation, which is on the right. And the main thing that we're looking for here is you can see that there's some gaps in the polymer chains, right? Now, those are places where you get an inadvertent increase in salt passage, especially for low molecular weight, uncharged constituents. And by closing those up, it doesn't significantly change your sodium chloride rejection, because your sodium chloride rejection is primarily held off from the surface charge of the membrane. But what it does change is the low molecular weight and or low surface charge compounds. So, when we try to look at compounds like that, a good example would be silica, right? If you compare a 720D, which is the yellow, the silica number there, to our newest generation of membrane, which is our TBW, you can see that the silica rejection is higher, even though the chloride of that TBW is actually lower. And that's because that TBW is an even lower energy membrane than the 720D. But its silica rejection is higher. And that's because its cross-linking is better, it's more complete. So that's allowing us to improve the rejection of these lower molecular weight constituents. And the reason that's important to us with this conversation is short chain PFAS, that's what we're talking about. Right? You're talking about compounds that are have very little or no surface charge and have very, very low molecular weight. It can be very difficult to reject. The one purpose of this webinar, though, wasn't just to talk about RO and how RO can reject it, because that's great. We've done this. We've separated these PFAS molecules out. But what on earth are we going to do with the brine, right? Because that's always, just we've moved the problem somewhere else, which is good, because in terms of handling high volumes of water, that's something that RO can do, right? And we've moved it to a much smaller volume of water. But I don't think that means that we're done. And that's a big thing that Zia is here to talk about, because from here, we need partnering technologies so that we are not just moving the problem downstream. We want to use RO to concentrate these PFAS, then use another technology to further concentrate, and then ultimately we want to get to full destruction. But you can't just use a destruction technology on the entire mass because of energy use considerations, et cetera. So with that, I'm gonna pass it over to Zia, and she's going to explain more what solutions might we have with the brine.
Great, thank you, Sean. Hopefully everyone can hear me. So with that, Sean hit the nail on the head. RO can take out PFAS and put it into a brine solution, which is obviously a smaller volume, higher concentration of PFAS in that brine. But then you've got this concentrated stream, which, what do you do with it? And there's a lot of questions in the PFAS world and treatment market on what do you do with it? Are you just shifting it from one stream to another? So hopefully I can get the slide to go. Might take a second. There we go. And so our focus today is going to be looking at on the water treatment side, so on the drinking water plant side, and really working to remove it from the drinking water, put it into a concentrated solution that we can then handle and protect public health. So protect our drinking water for all of us to continue drinking our tap without concerns. We do also see, right, PFAS is persistent, it's ubiquitous. There's studies showing it on Mount Everest from the ski wax and all of the protective clothing you have to wear out there, all the way down into the Marianas Trench in the crustacean. So it is everywhere, and we see it throughout the entire water cycle. We see it in stormwater, we see it in drinking water, we see it in landfill leachate, whether that's from contributors or if it's just stormwater falling on that landfill. And so we do really need to focus on a holistic solution that deals with PFAS once and for all. See if this will go. There we go. So with the recent regulations in 2024, EPA came out with interim guidance. Obviously, we also got the BOGO, buy one, get one deal of getting PFAS MCLs for drinking water, but as well as the hazardous designation under CERCLA. So with that, everyone's kind of figuring out, well, where do we put these concentrated streams, and what do we do with those? And the guidance currently is using, from the interim guidance from the EPA, is to use a hazardous waste landfill for concentrated streams, class 1 for non-hazardous. And I think we're all seeing that it's going to be an issue that persists. Oop. See. Okay, so if we're looking at PFAS destruction solutions, in the last 10 years, people have been working on new PFAS destruction solutions. It's really been accelerated in the last 5 years. And this is a study and maturity scale that GWI, Global Water Intelligence, came out with in 2022. Obviously, the market has changed. But from this 2022 scale of maturity for technologies, the most mature that they rated was electrooxidation. So at Ovivo, we have our O-Break commercially available. It is electrooxidation. I'm going to go a little more into detail on that, and when we will go over some of the other destruction technologies and just kind of their strengths and weaknesses, because each one of these fits a different water matrix. So again, this is from a study or survey done by CDM Smith in 2024. We did add a modification to it for electrooxidation, but essentially it just shows what waters match with what technology. And so for our intents and purposes with electrooxidation, we're looking at high salinity waters. Oop, there should be a box. Let's see. Anyways, we're looking at waters with higher salinity do quite well with electrooxidation, as it is a current-based technology, and so the higher salinity, the better conductivity you get, and so you have a more efficient treatment. However, it doesn't handle organics or solids as well, and it really does depend on the water treatment. So when we're talking about RO brine, electrooxidation appears to be a really good fit within that process flow diagram. Try to go to the next. So electrooxidation. O-Break is our electrooxidation technology. It is a electrochemical oxidation, or we just say electrooxidation. You pass a current through electrodes that are submerged in water. You have an anode and a cathode. And unlike electrocoagulation, where you have a sacrificial anode that dissolves into the solution and creates a flock and sludge, this is a non-sacrificial electrode. So your anode does not dissolve into solution, and it remains with your reactor for the lifetime of that electrode. And so it's a direct, oh, sorry about that. It's a direct oxidation that is the main mechanism of PFAS destruction. So it's directly happening at the surface of the anode. Electrical currents and oxidants come off of that anode. It interacts with PFAS, and we have a cleaving of the carbon-fluorine bond. So the higher concentration you have, the better contact with that anode you're going to get, and you get a better efficiency for destruction. Indirect oxidation also happens within the solution, where radicals and oxidants are created with that electron transfer into the solution, and those oxidants then break down PFAS into bulk liquid. It is not the main mechanism of destruction, but it is another reaction that does happen within the reactor. And one of the biggest positives for electrooxidation is that this operates at ambient temperatures and low pressures. Some of the other technologies out there operate at quite high temperatures and pressures to break down that CF bond quickly. It's a little bit slower with electrooxidation, but it is operated at ambient temp and pressure. So if we're looking at an on-site PFAS destruction approach, a holistic approach, we can concentrate it with reverse osmosis or O-lift, which is our film fractionation technology. We can destroy it with electrooxidation, and we can polish it with ion exchange and GAC. And by including this destruction, this concentration and destruction technologies in your process flow diagram, you end up extending the lifetime of your polishing step and therefore really minimizing your disposal costs and volumes that you're sending to the landfill or for regeneration. So our case study that we've been working on for some years now has been done at a drinking water plant. This is a 10 MGD surface water plant. They have MF and RO, which was installed in 2020, and we've been working on that our concentrate line. So looking at how do we pair technologies on the brine to extend the life of their GAC prior to discharge back into their local river. And with that, I'm going to move on to some data here shortly. So hopefully I don't bore anyone with data, but too bad it's the slides that we picked out. So with reverse osmosis only for concentration, if you're taking a treatment train approach, it's going to look like sending 10 MGD to your RO at 90% reject. So 1 MGD going to your electrooxidation. And then you would have your polishing step prior to discharge to the river, and 9 MGD going PFAS free out to distribution to your customers. So when we look at O-break with RO concentrate only, so there's no further concentration upstream. We have 2 electrodes that we look at that we have available with Ovivo. It's our MMO electrode and our BDD electrode. And on the left, we have MMO here. So you can see that we've got this first order reaction happening where you have an initial jump down in PFAS concentrations. Again, PFAS is y-axis, and then treatment time is on the x-axis. And then you kind of have this plateau where you're not seeing as much of a breakdown over time, and you're putting in energy, but you're not seeing as drastic of a treatment. Whereas with the BDD electrode, we see this 0 order, so somewhat more of a linear reaction destruction kinetics. And if we break this down for long chains versus short chains, our long chains on the left with the MMO again, we see the same trend, but we do see that over time, our long chains are actually still breaking down. It's more, we'll go to short chains next, but it's more of those short chains that end up being somewhat generated at the same time as destruction, right? Because as electrooxidation is happening, you are cleaving that carbon-fluorine bond, and you're going from longer chain to shorter chain to shorter chain to shorter chain, all the way down to mineralization. So it's important to evaluate electrooxidation both in long chains and short chains and see where exactly some of those reaction kinetics are slowing down. So on the left, MMO, we see, again, long chains are still breaking down. It is more of a plateau there in the middle, but then they continue to break down. And then on BDD, we have that 0 order, which mimics the total PFAS concentrations as well. And then if we go to short chains, hopefully, there we go. If we go to short chains, this looks very different. And again, it's that each step in the destruction reaction happens at a different kinetic timing, a different reaction time. And so our long chains with MMO, they're breaking down, but our short chains, they're being generated at about the same rate that they're being destroyed. So we don't see that decrease in concentration just because those reaction kinetics aren't happening at the same rate for the long chains. Whereas with the BDD electrode, we do see that breakdown is happening at the same faster than they are being generated. So we do see that concentration decrease over time. Oh, okay, great. That just emphasizes what I said. So then if we move on to with electrooxidation, there are byproducts. You are oxidizing water. There are byproducts generated. With this water specifically, we see perchlorate generated with certain electrodes. So with our MMO electrode, even though we kind of saw that plateau with the PFAS destruction, we have no perchlorates generated. Whereas with our BDD electrode, we do have considerable amounts of perchlorate generated over time. And that would be something that you would need to treat on the back end, depending on your limits and where you're using that water or putting that water. And then if we look at energy consumption, so this is our energy on the y-axis is in kilowatt per meter cubed of plant influent. And then we have our total PFAS reduction on the x-axis. And this is kind of getting at what I was talking about before with at a certain point, depending on your reaction kinetics, the water and the interaction with the electrodes, there is a point at which you have somewhat of a plateau or a diminishing return where you're putting in more energy, but you're not seeing that PFAS destruction happening at the same rate or with the same efficiency as before. So if we look at the MMO electrode, it's at about 50% of reduction is when you start of total PFAS reduction is when you start to see that diminishing return. And at that point, we would recommend that you send to polishing. Whereas with the BDD electrode, you can see that we're still getting quite a bit of total PFAS reduction. So it's at about that 90% total PFAS reduction is when we would recommend that you would send that to polishing. So if we're looking at the RO concentrate treatment train summary, this is the summary. This is our data. We have our top 6 up at the top there for viewing ease. I think it's 5, sorry, 5 up at the top there in bold for viewing ease with our RO concentrate. And then on the right, we've got a graph to easily view it. So you can see total PFAS. With our RO concentrate, we have about 850 or so ppt of total PFAS. With after destruction on that brine, we then get down to about 110, and then you send it to polishing. So the difference of what your polishing media would see here in this case is a difference of 8-fold roughly. With the RO concentrate, you would be sending that to the polishing versus this 110 ppt going to polishing. So you end up extending the life of your media for that polishing step, minimizing your disposal costs, minimizing your changeouts, and just continuing to extend that lifetime. So the next step is looking at pairing reverse osmosis with O-Lift, our foam fractionation technology. So this is going to be taking concentration step of RO and concentrating it even further. Foam fractionation is a great pair with RO concentrate. It utilizes PFAS's attraction to the air-water interface to remove PFAS through that attraction to a bubble. And so you essentially put air, or in our case, we can use ozone as well, into a column. It forms these bubbles, the foam goes up to the top, and you collect off that foam, and that foamate collapses back down into a liquid, and you treat that foamate. So the foamate generated in this process can be anywhere from 1,000 times more X in concentration to the RO concentrate, and it ends up being a volume of 1 to 10% of the influent volume. We've had plants where the piling is even down to 0.1% of the influent volume. So if you think about it as when you're going up to commercial scale, you would then be sizing a much smaller electrooxidation destruct step behind this on just that 1 to 10% of volume. So with our O-Lift system, we also can selectively use ozone. This reactor design is a continuous design, and we can selectively use air and ozone to create microbubbles. So with that, ozone is another oxidant, and so they have a higher overall surface area and an electrostatic charge compared to air. This significantly it boosts PFAS removal and concentration factors, especially when it comes to short chains. Short chains tend to not be as attracted to that air-water interface, and so with ozone, it increases that attraction to that surface. And then we'll see as well with ozone, we do see that downstream destruction and polishing is much more efficient as well with ozone. Okay, so this is our pilot system for O-Lift. And as you can see here in our pilot system, we've got our raw water going in. We have 3 reactors in our primary treatment train. So our water comes in, goes through 1 reactor, 2nd reactor, 3rd reactor, and then it goes out to your polishing media. The fomate from the first 3 reactors in series is composited into a tank. It all collapses back down into a liquid, and then we concentrate it up again in a secondary train. So in that secondary train, we end up stepping up the concentration even further. And that fomate then we send to destruction. So if we're looking at the full treatment train process flow diagram, you have your RO up front, taking account, it's about 90% reduction in our case for this case study. Our 1 MGD goes to foam fractionation, and we get about 1%, an approximate 1% or less than going to electrooxidation in the form of fomate. So you end up with sizing your electrooxidation for that 1% of the 1 MGD rather than the full 1 MGD here. And then the clean treated water from foam fractionation would go to your polishing media. And one of the treatment options that we're also have been working on and looking at and continue to pilot is recycling that destructed water from the O-break. So by sending it back to the front of O-Lift, you then can concentrate it back up again, go through the destruction step, and recycle it to the front end. So instead of sending that water to your polishing step, you can continue to concentrate and destroy and concentrate and destroy. That destruction step makes it this possible with that mass balance in mind. Okay, so we're going to look at foam fractionation data from our RO concentrate in to the foam fractionation or O-Lift system. This is our average PFAS removal, and we've got highlighted here the 5 main ones that are regulated. So PFOS, PFOA, PFNA, PFHXS, PFBS. And you can see that we've got high PFAS removal, even for some of the short chains. 90% with PFBS, PFHXS, we've got 97%, PFNA, we have 94%, PFOA, 98% removal, and PFOS, 97%. So you can see that we're getting really high PFAS removal from our influent RO concentrate. And then in terms of volume reduction, we also see a massive volume reduction. So it's a 99% volume reduction, meaning you end up sizing that O-break system for that 1% rather than the full RO concentrate line. And lastly, I just want to highlight on this the amount of concentration factor you're getting here. So again, with electrooxidation, that direct contact with the electrode is the main mechanism of PFAS destruction. So the higher concentration you have in your stream, the better and more efficient the electrooxidation is going to do on that. So again, with the RO concentrate, we had somewhere around 1,000 ppt, and then with this fomate, we end up with 38,000 ppt of total PFAS. So now we should be, oh, it's got it highlighted. We should be moving on to looking at destruction data on this fomate. So again, we've got the same setup as before, the MMO electrode on the left and the BDD electrode on the right. And we see different reaction kinetics than we did before. So we're seeing similar reaction kinetics with that first order kinetic breakdown. So with, let's see if it's, oh no, we go straight to energy. And with this is just partially in fact due to we have a lot more PFAS that you can analytically see and detect and look at, but we do see again first order on the left and first order on the right with MMO and BDD respectively. So if we move to energy consumption and total PFAS reduction percentages, we're seeing very similar reaction kinetics with the fomates here. So with both electrodes here. So with both of them, we would probably recommend roughly the same. So somewhere between 85 and 90% total PFAS reduction is about when you would want to send that to polishing or recycle it back to the front end of your O-lift. And if we're looking at a summary of the treatment train, this is what it looks like. So our RO concentrate comes out somewhere around the 800 to 1,000 total PFAS PPT. Our fomate then is boosted up to 56,000 PPT, and then post-destruction we get down to about 5.5 thousand PPT. This then can get recycled back to the front of the O-lift, and you would then be concentrating it back up in your fomate and not sending that to polishing. So just to wrap things up on the PFAS destruction side, PFAS removal is a huge municipal issue that needs solving. I think we're all in the same boat on that, especially with the 2029 deadline to have everything in place for our MCLs. RO is in the primary position for large-scale robust PFAS removal and concentration. And with Sean's presentation at the beginning of this, just going over the details of PFAS removal by RO, it is a great fit for large streams. RO applications must have a solution not only to remove PFAS from the concentrate, but we have solutions for the brine as well. So electrooxidation for PFAS destruction is a great technology that pairs well with that high salinity from the RO concentrate. And it's positioned for safe on-site operations by water treatment operators. When you couple it with more upstream concentration, destruction is higher energy efficiency and cost efficient. And we have the right tools, and it's time to implement what we've learned in society to solve this critical problem. I don't know if there's another slide. Oh, okay. I might have skipped it. Sorry.
Excellent. Thank you, guys. Thank you, Zia. Thank you, Sean, for that. I'm receiving a few questions in here. So let's see what we've got here. You guys can still submit questions. It's in the control box there for you in the control panel. So feel free to keep submitting questions while we answer some of these. My first question, it looks like, is for Sean. Are there existing plants using Toray RO that are already in use specifically for PFAS removal?
Yes, there are. And in fact, many of you that are on this call are AMTA members, but AMTA held a joint AMTA-CETA conference in Alabama where we actually toured 10 MGD facility that is treating PFAS with Toray RO. So yes, those exist. That plant's been running about 3 years, and it's there's some other plants out there as well that we've worked on, and quite a few more than that. There's a lot of applications where we're piloting currently as well.
Excellent. I've got another one here. Is PVDF considered a PFAS?
So according to the US EPA's current definition of what a PFAS is, no, PVDF is not in that family of chemicals. And actually, same comment for those of you that are AMTA members. If you're not a member, I would encourage you to become an AMTA member. But there is a paper that we gave in the AMTA conference in Racine that specifically addressed that issue. And so if any of you are curious about that issue, you can use our contact information on the screen, or if you're an AMTA member, you can already go in and look at past proceedings. I think the name of that paper was PVDF as a PFAS or something along those lines.
Sounds good. I'm going to stick on the RO train, and I think then we'll move over to you, Zia, after this. Do you expect NF to be used in addition to RO for PFAS rejection?
I'm sorry, can you say that again?
I can. Do you expect NF to be used in addition to RO for PFAS rejection?
Yes, in some cases. NF is an effective tool that's in our toolbox here, and rejection of some of the long chain PFASs can be quite good with the tighter nanos. But I would say that if it depends on application, right? If removal needs to be higher, or if the short chain is a bigger contributor to the problem, or a major contributor to the problem, the ROs, and specifically the newer ROs that I mentioned, are going to be much more effective at removing the shorter chain PFAS constituents.
And then Sean, is multi-stage RO a viable option for volume reduction?
Yeah, certainly. We see most RO plants are, 2-stage up to about 80 to 85% recovery, and 3-stage if you're above 85% recovery. Seen as high as 4-stage. Normally with RO, we're trying to remove dissolved salts, right? In the case of PFAS treatment, we might not have as many of those dissolved salts, in which case higher recoveries might be possible in a lot of these waters because they're not normal RO candidates. And as such, if the sparingly soluble substances aren't as high, higher recoveries than that are even possible, and you could hypothetically go to a 4-stage RO. I don't know. And I think, I'm answering the question about stages, and I'm wondering if maybe the question was meant to also ask about potentially more than one pass. So the difference between stage and pass being, with multiple stage, you're concentrating your concentrate. With multiple pass, you're taking the permeate from one pass and you're putting it through RO again, and further purifying it. You could do both. You could also do more than one pass, but if I think your initial PFAS concentration would need to be really, really high for you to need that second pass. I think that would be unlikely, but you could do it, yes.
And one more question here: does PFAS foul membranes?
That's a good question. I suppose if you had high enough concentration, and depending on the PFAS, it's hypothetically possible, right? Surfactants can sometimes act as a foulant, but we've honestly not seen that so far to date. With the work that we've done with it, we've not before seen PFAS be a foulant problem.
Excellent. Zia, your turn. Are the anodes consumable, like the electrocoagulation?
Yeah, so the anode is non-sacrificial, so they should last the lifetime of the electrode package as a whole. So they don't dissolve into the solution, and they do last the full lifetime of that electrode.
This follows right behind that. Do your electrodes foul? Is the scale an issue? How does electrochemical oxidation compare?
Yeah, so for scaling, there are a couple of management techniques that we use for scaling on electrodes. The main one is reverse polarity. So by switching the polarity between the anode and cathode, you push off any scalant, and you just continue to use that reverse polarity. We determine the optimal operation parameters for that reverse polarity mechanism by piloting.
Excellent. How does the electrochemical oxidation compare to other PFAS destruction technologies that I hear about, i.e. superficial water oxidation, halt, incineration?
Yeah, I think one of the main pros for electrooxidation is that it can handle high salinity waters, whereas those waters with high salinity don't handle as well and precipitate out those salts with stuff like supercritical water oxidation and halt struggle with that matrix of water. So for electrooxidation, it handles those high salinity waters quite well. It just increases conductivity and increases energy efficiency within the water.
Awesome. I've got here, what other byproducts are formed during the electrooxidation? Can you balance on it? Can you do a balance on it?
Yeah. So that's a great question. Obviously, perchlorate is one. It's an oxidation process, so anything that can oxidize will oxidize. So we do see that metals will oxidize, things like COD, those oxidation happens there, and we even see that even on the O-lift process as well in foam fractionation. So byproducts are going to be those oxidation byproducts.
Excellent.
In terms of balancing fluoride, it's tricky to do that because there's so much transformation, but we have utilized some of the other tools in the analytical toolbox, so things like AOF and TOF, or total organic fluorine, and as well as top assay, and looking at that. I think there might be another question about those methods in here.
Yeah.
If you don't mind, I'll ask.
No, go for it. Yeah, because you're seeing them too. So.
Yeah. So I see there's another question in here. Also, have you done any other PFAS analyses such as AOF and top assay? If so, what did those results look like? So we have done that fluoride testing. So that's AOF, TOF, and you do a calculation to get that PFAS related fluoride. It's with the concentrations we're working at, it's actually quite difficult to get that analytical method to test down to the levels we're at. So we haven't had the most success with AOF, TOF, but we do use those, and it just depends on the application and the concentration ranges we're in. And then for top assay, we actually use top assay quite a bit, especially when we're looking at the electrooxidation side of things. So for the case study I just talked on, we have quite high precursors for 6.2 FTS, which is kind of an odd one, but for this region, 6.2 FTS is really part of their water there. So with that top assay, you take a sample, you analyze with, typically it's 1633. You then go through a oxidation process with heat and persulfate, and then you analyze the post oxidation sample again with, typically it's 537. And so you can see this delta of what PFAS precursors you might have in your water, right? There's thousands of PFAS compounds. We're still finding new ones that analytically we don't see with the traditional methods. And so top assay is a great tool in the toolbox for especially electrooxidation to understand how much are we actually having to oxidize. Because with your traditional method, like 1633, you might just see 10 PPT PFAS, that's not, but like 10 PFAS. Whereas if you're looking at top assay, you might actually have 15 or 20, and you're not just oxidizing those 10, you really are oxidizing the full water matrix. So you're really oxidizing that full 10 or that full 15 or 20 or whatever it is. So we do use top assay quite a bit, and we do, depending on the water, use AOF and TOF.
Excellent. Thank you.
I can answer the one question here. I see what, similar to the fouling question. Does any of the PFAS change actually stick to the membrane? And then what to do with the old membrane? Sort of along the lines of the fouling comment, we've not seen significant buildup through fouling or buildup on the membrane layer of these PFASs. So we haven't seen that to date. So to our knowledge, there's not an inherent issue with that. And it's something that we've been looking at a lot in a lot of our testing, is looking at the mass balance, right? Does the concentrate and permeate, total match your feed? And that's giving us some clues as to how that separation mechanism is working. But we've not seen that be a problem to date, and I would speculate that you wouldn't have a disposal issue with old membranes that did separation, because the whole point of the RO is to keep it in solution, keep it liquid to liquid.
Perfect. So yeah, if you see any others, there's a lot of questions here, so I'm slowly making my way through.
Yeah, I will go ahead and answer. There's a question on, did the surfactant load affect electrooxidation? So this brings up a point that I didn't quite cover in the presentation. Some waters don't naturally foam, and so you have to add a surfactant to boost foaming capabilities, foaming potential in that water. With this RO concentrate, despite the PFAS concentrations, it doesn't foam, and it actually, with some of the shorter chain PFASs, having that surfactant increases that attraction to the bubble interface. So we do use a surfactant on this case study for foam fractionation for O-lift. In the sense of affecting electrooxidation, there's kind of two pieces to it. So if you have foaming, and foamate is foamy, so if you have foaming when you go to electrooxidation, it can hinder that direct contact with the electrode, and that being the main mechanism of PFAS destruction, we use defoamers. And again, you have to determine that concentration and optimization by piloting and learning what your water is really going to look like. So we use defoamer to combat foaming at the electrode. And then the other piece of it is electrooxidation. When it's cooking, it's going to oxidize the surfactant. So you do end up having surfactant breakdown. So it is just another piece that has to be oxidized alongside the PFAS molecules. So hopefully that answers that one.
Perfect. And I've got one last question. I think both of you can take your turn on answering. Essentially, how do we learn what is possible for our projects?
Good question. I can start with that. I mean, we're doing everything case by case right now. It's an emerging market, of course, and we're definitely not publishing everything that we know, and not talking about everything that we know on webinars. But yeah, please, if you've got a project, or you're not sure if this is a good way for your project to go, we'll be quite honest, and when I showed the map of how many, applications that are going to need some sort of PFAS removal out of the drinking water, and the number of applications is absolutely massive. Do I think all of those are going to go RO? No, of course not. But might a lot of them? Yeah. And each of them are different, because each of them have different mixes of long chain, short chain, etc., and their treatment water quality goals, and maybe what else they might want to get out of the water as well, and or remineralization concerns. So we would want to take all of those into account in providing technical support to anyone who's looking at this for their municipality or industrial project, or whatever the case may be. But we want to be a key solutions provider here. Our team, we have a large team of engineers that is available to help with these projects. So, please reach out to us if you've got some interest or have some needs, and we'll try to best delineate where we think we can help and where we might not.
and my answer is going to be somewhat similar to Sean's, is determining a good fit and a good solution. It's going to mean piloting with electro-oxidation, with O-break, O-lift. It's going to mean doing bench testing or piloting to figure out the best fit. And yeah, there are some waters that don't fit our technologies, and we'll let you know up front, hey, this just doesn't fit the matrix that our technologies can handle. But we've got, same as Sean, a team of people who work very hard on this and can give you answers pretty quickly on what fits and what doesn't fit, and your options for figuring out a well-optimized, efficient system. But Aviva definitely strives to be a solution provider, and not just one technology, but multiple that can get you to your ultimate treatment goals.
Awesome. Thank you, Sean and Zia, for presenting today and all your knowledge. If any of you guys have questions, you can scan those QR codes. Katie was supposed to present. Thank you, Zia, for filling in for her. But any questions, if you guys still have, feel free to reach out to Sean and Katie. And Zia, we don't have your info, but we can share that with people if they want it.
Ask Katie as many questions as you want.
In just a moment, a survey will be displayed. We would appreciate your feedback. It'll help us improve future sessions. Toray would like to thank AMTA for putting this on. And on behalf of AMTA, Toray Membrane USA, and our presenters, thank you all for joining us today, and enjoy the rest of your day.